Ever wonder how we get from just a spark of an idea to some world-changing discovery? Well, it's definitely not magic. It's a process. It's a set of rules, really, that are the bedrock of all science. And today, we're going to break down the absolute fundamentals of measurement. So here's the big question, right? How do we prove something is scientifically true? I mean, it's not just about guesswork or having a hunch. Science gives us a roadmap, a really structured and repeatable process that helps us separate fact from fiction. And it all kicks off in one very specific place. All right, section 1. Every single scientific journey, I don't care if it's figuring out why an apple falls from a tree or landing a super complex rover on Mars, it always begins with the same simple thing, a question. Just plain old curiosity. Okay, so for our explainer today, we're going to tackle a question that's super simple, really clear, and most importantly, perfectly testable. We're going to investigate springs. So when we add weight, or what scientists call a load, to a spring, does its length actually change? Now, you might be thinking, well, duh, of course it does. But here's the thing about science. We don't assume, we measure. So this is that roadmap I was just talking about. Scientists followed these steps pretty rigorously to make sure their answers are reliable. We've already done step 1. We identified our problem, the spring. And we could even form a hypothesis, an educated guess that might sound something like, yep, the more load you add, the longer the spring gets. The rest of these steps, well, that's how we turn a simple guess into a solid fact. Okay, next up, before we can even think about planning our experiment, we have to learn to speak the language of science. And that language really is built on one thing, measurement. It's how we take things we just see and turn them into cold, hard data. So, the core vocabulary word in this whole language is something called a physical quantity. And honestly, it's a really simple but super powerful idea. Basically, if you can measure it, it's a physical quantity. Things like length, time, temperature, weight, these are the actual words we use to describe the world in a scientific way. And this slide really shows you the beautiful structure of that scientific language. On the left, you've got base quantities. A great way to think of these is like the alphabet. They're the fundamental building blocks, things like meters for length or kilograms for mass. Then, on the right, you have derived quantities. These are like the words we create from that alphabet. Area, that's just length times length, or meters squared. Velocity is just length divided by time, or meters per second. See how it works? It's all built from just a few simple fundamental pieces. Okay, let's move on. We have our question, and we have the language to describe what we're going to see. So now comes the really crucial part. How do we design an experiment that actually gives us an answer we can trust? And here's the thing, for our results to mean anything at all, we absolutely need what's called a fair test. I mean, think about it. If we're testing our spring, we can't just hang weights on it in a hot room one day and then do it again in a freezing cold room the next, right? We have to be disciplined. And that discipline really boils down to one simple concept, controlling the variables. First step, we have the manipulated variable. Think of this as the star of the show. It's the one and only thing that we are going to intentionally change just to see what happens. So, in our spring experiment, what is it? It's the load. We're going to systematically add more and more weight to that spring. Next, you've got the responding variable. This is what we're watching. It's the result, the effect that we're hoping to measure. So, as we change the load, we're going to be carefully measuring the length of the spring to see exactly how it responds. And this one, this is the real key to a fair test, the constant variable. This is basically everything else that we have to lock down and keep exactly the same. For instance, we have to use the very same spring for every single measurement. We should probably do the experiment in the same spot at the same temperature. But why? Well, imagine if we changed the spring halfway through. How would we know if the change in length was because of the new load or because of the new spring? We wouldn't. No way. So keeping these things constant is what lets us isolate the one relationship we actually want to study. All right, so we've got our fair test all designed. Now it's finally time to measure. But here is a reality check. Not all measurements are created equal. The quality of our tools, and just as importantly, the words we use to describe that quality, are absolutely critical. Now this table is great because it breaks down 3 words that people mix up all the time: accuracy, precision, and sensitivity.
Let's start with accuracy. Accuracy is all about hitting the bullseye. How close is your reading to the actual true value? Then there's precision. Precision is all about consistency. Your readings might be way off the true value, but if they're all clustered tightly together, hey, that's precise. And finally, sensitivity. This is really about having the right tool for the job. A super sensitive micrometer can detect tiny, tiny changes that a regular ruler would completely miss.
So in a perfect world, right, every single measurement we took would be absolutely perfect. But newsflash, science happens in the real world, and we'd have to be honest with ourselves. Errors are just a natural part of the process. The real key isn't to pretend they don't exist, but to understand them.
And errors really come in two main flavors. First, you've got systematic errors. These are consistent, they're repeatable. A perfect example is a ruler that doesn't actually start at 0. The error is literally built into the system. The good news is, if you know about it, you can often correct for it. Then, on the other hand, you have random errors. These are completely unpredictable. A tiny shake of your hand, a little gust of wind. These things cause small, random hiccups in your readings. So the big question is, how do we fight back against these errors? Well, we use strategy. The single best way to deal with those random errors is to repeat your measurements over and over, and then just calculate the average. That smooths out all those unpredictable highs and lows. You can also improve your data by using more sensitive instruments. And, this is a big one, always make sure your eye is level with the scale. If you look from an angle, the reading can look different. That's a classic mistake called parallax error, and it's actually super easy to avoid once you know about it. All right, let's wrap this up. We started with a really simple question about a spring, and we've walked through the whole process of designing a fair test and really getting into the nitty-gritty of measurement. So now, let's zoom out a bit and talk about why any of this really matters. Because here's the crucial takeaway. These rules, they're not just for a classroom science experiment. The exact same principles, defining what you're measuring, controlling your variables, obsessing over accuracy, and fighting errors, these are the very same things engineers use to build skyscrapers and doctors use to figure out the right dose of medicine. This stuff is the universal foundation for pretty much all technology and discovery. When you get right down to it, it all boils down to this. If you can't measure something reliably, you can't really understand it. And if you can't understand it, there's no way you can improve it. Measurement is always, always the first step on the path to mastering, well, anything. So, I'm going to leave you with a question to chew on. Think about your own life. What's the absolute best way to brew your morning coffee? What's the fastest route to get to work? By identifying the variables, measuring the outcomes, and running your own little fair tests, you can apply this powerful scientific framework to just about anything. So, what are you going to measure first?